6 million purple sea urchins have been systematically crushed on the ocean floor over a period exceeding 10 years. Why would such a massive biological intervention be necessary in a natural environment? It seems simple to assume these creatures are invasive or possess some form of toxicity that endangers other life, but in reality, their presence is merely a physical symptom of an entire ecosystem that has drifted out of its delicate mechanical balance. Off the coast of Southern California, towering forests of giant macrocystis kelp once rose 30 meters from the seafloor toward the surface. One can notice how these massive stalks formed a complex underwater city, providing a physical structure that sustained more than 700 distinct species. Yet, within a window of just a few decades, over 80% of this living canopy vanished completely. In its place are barren, rocky seafloors carpeted entirely with sharp purple spines. Scientists classify these zones as urchin barrens, which are effectively biological deserts beneath the surface of the sea. The process of degradation is only gaining momentum as the urchins consume every new sprout of kelp before it can take hold. One can notice how the equipment used by divers systematically clears these rocky surfaces. It is visible how the removal of these organisms allows the sunlight to reach the seafloor once again. But this is just the beginning. The transition to the next level of restoration requires more than just mechanical clearing of the desert. Everything only gets more complicated when analyzing the timeline of the collapse. An ecosystem that endured for centuries fell into total decline with staggering speed. It only looks obvious that removing the urchins is the solution, but in reality, the forest remains trapped in a state of stasis until the grazing pressure is eliminated. The camera glides along the jagged rocks where millions of urchins once sat side by side. The process of crushing these organisms releases nutrients back into the immediate environment, while clearing space for kelp spores to settle. It does not end at this stage, as the recovery of the kelp requires the absence of predators to reach its full 30-meter height. Thus, the clearing of the seafloor concludes this phase, opening the road to the regeneration of the underwater canopy. 30 meters is the height reached by the golden-brown fronds of Macrocystis porifera as they rise from the cold Pacific seafloor toward the sunlight. Why did these underwater forests become one of the most productive ecosystems in North America? The sheer speed of their development is difficult to match in the terrestrial world. Under ideal conditions, these giant kelp plants can grow up to 60 centimeters in a single day, fueled by nutrient-rich ocean currents flowing in from the deep offshore. By the middle of the 20th century, tens of thousands of hectares of these forests line the California coast in a dense, three-tiered structure. One can notice how the fronds interweave to resemble a complex woodland, but this was more than just a habitat. It was a fully functioning ecological infrastructure that provided breeding and feeding grounds for more than 700 species of fish, invertebrates, marine mammals, and seabirds. The process is only gaining momentum as the kelp performs mechanical functions for the coastline. Beyond supporting biodiversity, the kelp forest served as a massive natural coastal defense system. It is visible how the dense biomass absorbs the force of winter storms and reduces shoreline erosion by trapping sediments. This mechanical filtration helped clarify the water, while the plants simultaneously stored carbon within their tissues and the seafloor sediments. For generations, the Tongva and Chumash indigenous communities harvested this resource for food and tools, later followed by a commercial industry producing fertilizers and food thickeners. It seems simple for such a vast system to endure, but in reality, the ecological balance was slowly tipping out of equilibrium. Offshore surveys conducted near Palos Verdes in the early 2000s revealed a staggering figure. More than 80% of the kelp forest canopy had vanished entirely from the region. Satellite images that once captured shimmering golden patches on the ocean surface now showed scattered dark gaps. This indicated that the bare rock of the seafloor was no longer covered by vegetation. The collapse did not stem from a single shock, but from a chain of pressures that had been building for years. Runoff from the Los Angeles watershed carried sediment, heavy metals, and various pollutants into the sea. These materials smothered the rocky reefs where kelp spores need to anchor and germinate for the next generation. At the same time, coastal construction increased water turbidity, which blocked sunlight from reaching the seafloor and constricted the vital process of photosynthesis. Everything only gets more complicated as biological controls fail. Overfishing rapidly depleted key predators within the local food web. Large fish, lobsters, and other species that feed on sea urchins declined sharply, breaking the natural control mechanisms of the ecosystem. Without predators, urchin populations grew unchecked, consuming the remaining kelp at the roots. One can notice the transition to a barren landscape as the balance of species shifts. Successive marine heat waves then struck struck the weakened environment. Between 2014 and 2016, the phenomenon known as the blob event caused Pacific surface temperatures to rise abnormally across vast areas. Giant kelp, which is biologically adapted to cold water, endured prolonged thermal stress. Growth slowed significantly, and the ability of the forest to regenerate weakened until the structure could no longer sustain itself. Layer upon layer of environmental pressure pushed the ecosystem further away from stability. As the physical forest structure disappeared, the complex habitat for hundreds of specialized marine species disappeared with it. The underwater landscape transitioned from a lush, three-tiered forest into a silent, rocky expanse. This marks the end of a long period of ecological productivity along the shoreline. 150,000 to 300,000 sea otters once densely inhabited the Pacific coastline, stretching from Alaska down to Baja California. This was the state of the ecosystem before the 18th century, when these animals functioned as the primary guardians of underwater forests. Why did such a vast population nearly vanish from the face of the earth? The answer lies in the fur trade boom of the 18th and 19th centuries, which systematically devastated their numbers across the entire region. By the early 20th century, these marine mammals had almost completely disappeared from California, with the population declining by more than 90%. It only looks obvious that the loss of one predator would be manageable, but in reality, this triggered an ecological collapse. Only a few dozen survivors were eventually rediscovered in 1938 off the coast of Big Sur. Ecologists today classify sea otters as a keystone species because their biological influence on the environment far outweighs their actual numbers. An adult otter can consume up to 25% of its total body weight every single day. One can notice how this relentless appetite translates into the removal of 2 to 4 kilograms of food per individual, consisting primarily of sea urchins and various shellfish. The process is only gaining momentum as research highlights the sheer scale of their impact. Studies show that in geographic areas with stable and healthy otter populations, sea urchin densities are often 10 times lower than in territories where otters are absent. This constant and heavy predation pressure allows the kelp to grow undisturbed and rebuild the complex forest structure beneath the waves. Today, the sea otter population in California has recovered to approximately 3,000 individuals, but these groups are mostly concentrated along the central coast. They remain largely absent from Southern California, which is the exact region where kelp forests have suffered the most severe and visible declines. But this is just the beginning of the imbalance. Their absence is not merely the technical loss of a single species, but the total removal of the highest level of control within the marine food web. Everything only gets more complicated as the ecological pressure shifts. When the forest guardians disappear, the pressure does not vanish from the system. Instead, it moves downward toward the seafloor. If sea otters functioned as the air force controlling the upper layers of this aquatic ecosystem, then the sunflower sea star served as the special operations unit of the seabed. It was one of the largest and fastest sea stars ever recorded along the Pacific coast, boasting an arm span reaching nearly 1 meter. It is visible how its 20 to 24 flexible arms allow it to glide with surprising speed across rocky substrates. At first glance, sea stars are seen as slow-moving organisms, but in reality, the sunflower sea star was a highly mobile predator. To sea urchins, these creatures represented a constant nightmare. The mere chemical scent of a sunflower sea star could cause urchins to scatter in all directions, which immediately relieved the kelp holdfast from relentless grazing pressure. The process of protection was interrupted in 2013 when a mysterious epidemic known as sea star wasting disease erupted along the west coast of North America. White lesions appeared on the bodies of the sea stars as their tissues began to decay rapidly. One can notice how the arms detached from the central discs, and within a matter of days, the animals disintegrated into pale, formless masses on the ocean floor. From the cold waters of Alaska to the warmer coast of Mexico, sunflower sea star populations plummeted by more than 90%. In many specific parts of California, they vanished entirely from the ecosystem. This sudden collapse created a profound and dangerous ecological void. When the king of the seafloor disappeared, the sea urchins were no longer hunted by their primary subterranean adversary. This absence became the critical tipping point that prepared the environment for the next phase of ecological tragedy. The material remains of the former forest now lay vulnerable to an unchecked explosion of herbivores. 10,000% is the staggering rate at which purple sea urchin populations surged as their natural biological barriers collapsed one after another. together. Why did these creatures suddenly transform from secluded reef dwellers into an unstoppable force of destruction? For decades, they remained hidden within rocky crevices to feed on drifting kelp fragments, but the ecological shift forced millions of urchins onto open reefs in a desperate search for sustenance. The process is only gaining momentum. One can notice how the urchins crawl directly onto the kelp holdfasts to gnaw through the root-like anchors securing the plants to the seafloor. This action causes towering columns of kelp, often reaching heights of 30 meters, to detach and drift away with the ocean currents. This leads to the formation of urchin barrens, which are vast, pale expanses where the seafloor has been stripped entirely bare of vegetation. It seems simple to assume the urchins would eventually starve. In reality, these organisms possess an extraordinary physiological resilience that allows them to endure for years without a stable food source. When nutrition becomes scarce, they enter a state of starvation survival by shrinking their internal organs and significantly lowering their metabolic rates. These individuals are technically known as zombie urchins, which possess almost zero nutritional or commercial value, but remain capable of devouring every new kelp sprout the moment it appears. Biological productivity plummets in this extreme state as the forest structure disappears. One can notice the gray rock surfaces becoming carpeted with thousands of purple spines packed together as tightly as industrial gravel. To prevent the total loss of the kelp forests in Southern California, the Bay Foundation initiated a massive direct intervention project on the United States West Coast. They abandoned the strategy of waiting for a natural correction in favor of physical removal by hand. It gets more complex further on. Thousands of hours of underwater labor were required to implement this strategy in environments characterized by low visibility and strong hydraulic currents. Since 2013, commercial divers and trained volunteers have descended onto the rocky reefs around the Palos Verdes Peninsula. Using hammers and specialized technical tools, they systematically reduced the density of the purple sea urchin populations across the affected zones. The goal was not total eradication, but a precise recalibration of the ecosystem. Based on extensive field data, technicians established a specific target threshold of approximately 2 urchins per square meter. This is the density low enough to allow kelp to anchor and grow at a rate faster than it can be grazed down by the remaining organisms. One can notice the deliberate pace of the divers as they clear the reef millimeter by millimeter. Everything only gets more complicated as the project expands. The Foundation partnered with marine protected areas to safeguard rockfish and other native species that act as natural biological controls. This ensures that the recovery is supported by the return of predators that naturally manage urchin numbers over time. It is a labor-intensive and costly battle against ecological decline, but this is just the beginning of the recovery phase. Each square meter of returning kelp serves as physical evidence that science-based intervention can successfully reopen a path towards stability. The forest structure gradually reappears as the fronds reach toward the surface once again. Thus, the ecosystem reaches the standard ready for the further stage of natural development. 6 to 12 months is the exact window required for the seafloor to begin its physical transformation after the density of sea urchins is reduced. Why is such a rapid reduction in these herbivores necessary for the environment? At first glance, the urchins appear to be a natural part of the seabed, but in reality, their overpopulation prevents any vegetation from taking root. Once their numbers are lowered, the kelp forest begins to rebuild its vertical canopy structure with remarkable speed. The process is only gaining momentum. 50 to 80% is the measurable increase in canopy cover recorded in the offshore waters near Palos Verdes after only a few growing seasons. One can notice how the thick stalks reach toward the surface, creating a complex three-dimensional habitat where nothing but bare rock existed before. This structural change triggers a cascade of biological returns. Underwater surveys indicate that fish densities in these restored zones are now 2 to 3 times higher than in the surrounding urchin barrens. It is visible how the biomass of rockfish and reef fish increases significantly within a period of just a few years as the forest provides shelter and food. Even the commercially valuable red sea urchins demonstrate a shift in their physical state. Their reproductive condition improves as gonad mass indices increase several-fold compared to the previous biological desert phase. But this is just the beginning. Carbon absorption represents a less visible but technically significant impact of the forest revival. Giant kelp grows with extreme rapidity and accumulates substantial biomass in a short time frame, which allows it to sequester carbon within its plant tissues and the seafloor sediments. The equipment monitoring chemical levels shows how this recovery buffers ocean acidification at a local scale. This stabilization of the water chemistry creates more favorable conditions for shell-forming species such as mussels, clams, and especially abalone. These organisms are highly sensitive to even minor chemical shifts in the seawater. The deep green stretching across the ocean surface serves as physical proof of ecological resilience when the pressure of overgrazing is removed. Transition to the next level. California is now serving as a reference model for coastal regions worldwide where similar ecosystems face their own environmental crises. The restoration techniques developed here are being analyzed for implementation in diverse maritime zones. Thus, the material for global ecological recovery is being prepared through these localized successes. 35 million tons. This is the scale of global farm seaweed production currently reaching international markets every 12 months. Why has this marine resource become the focal point of a $20 billion industry? At first glance, seaweed appears to be a simple biological organism drifting in the currents, but in reality, it represents 95% of the total commercial supply, growing at rates that outpace almost any land-based crop. In nutrient-rich cold zones, one can notice the golden fronds expanding by tens of centimeters in a single 24-hour cycle. Cultivation begins with the deployment of complex suspended long-line systems beneath the ocean surface. Submerged cables stretching hundreds of meters serve as the foundation for seeded strands. The equipment gradually stabilizes these lines against the pressure of the tides. After a period of 4 to 6 months, the biomass reaches its optimal harvest size. Specialized vessels then haul the heavy cultivation lines to the surface, with the steady hum of mechanical winches. Crew members cut the seaweed and move it into storage holds for transport ashore. The process is only gaining momentum. Specialized shore facilities receive the raw material for washing, sorting, and preliminary processing. One can notice how some batches lay in even layers for natural sun drying, while others move directly toward industrial processing plants. Aquaculture reduces the physical pressure on natural coastal ecosystems by providing a stable year-round supply of raw material without depleting wild kelp beds. It is visible how this creates a predictable production chain. Everything only gets more complicated as the material moves from the ocean floor to the industrial laboratory. Sodium alginate extracted from kelp is now being transformed into high-tech biodegradable coatings. Scientists from Flinders University and the German firm CH Bioforce have engineered a bio-based film capable of fully decomposing in natural environments. This material offers oil resistance, moisture protection, and heat tolerance comparable to petroleum-based plastics. The process does not end at this stage. It serves as a critical alternative for plastic linings and food packaging in regions like Namibia, where bans on plastic straws and bottles are already in effect. Can seaweed effectively replace the massive volume of synthetic waste currently washing ashore? The question remains central to the development of the blue-green economy. Transition to the next level involves the production of biofuels and livestock feed additives designed to suppress methane emissions. Laboratory sensors record the precise chemical shifts required to turn raw kelp into industrial-grade bioplastics. Biology and industry are no longer separate domains, but interconnected components of a single economic ecosystem. Thousands of hours of manual labor on the seafloor have allowed the golden columns of kelp to rise once again off the coast of Palos Verdes. This recovery is the product of deliberate scientific intervention rather than environmental luck. It is visible how the ecosystem rebounds once the critical links in the chain are restored. The cost of waiting for natural recovery consistently exceeds the investment required for active industrial and ecological management. From a forest once locked in decline, an entirely new value chain is emerging from the cold waters of the Pacific. The material is ready to move to the next processing phase without haste. Thus ends one of the key stages of steel production.